we're going to look at one more non-example of a vector space. So suppose V is the set of integers, and this set has normal vector addition, meaning that we add two integers just like we would do normally. 3 plus 5 is equal to 8, which is the same thing as 5 plus 3. But our scalar multiplication, well, our scalars, remember, if I don't say where they're coming from, you assume that they're coming from the real numbers. The scalar multiplication is defined in a funny way. We say that alpha times k, where k is an integer, and I'm using this funny multiplication because I don't want you to get confused with the normal multiplication. We're going to let it be equal to, you have this notation, which is the greatest integer less than or equal to alpha times normal multiplication, that integer. So let me show you what I mean by giving you an example. So you take a real number, because that's where the scalars are coming from. So this is a real number, and you multiply it with an integer, because scalar multiplication says we have a vector here, and our vectors are coming from the integers. This is equal to this funny notation with 2.25 times 4, and then it's the floor function. The greatest integer less than or equal to this number is 2, so we put 2 here, and then 2 times 4 is equal to 8. So that's how you're figuring this one out. So if you have 3.99 times negative 1, this is going to be equal to 3 times negative 1. Put this circle notation so we don't get confused with the multiplication, because the greatest integer less than or equal to this is 3, and we get negative 3. So let's show that this is actually not a vector space. This set of integers with this scalar multiplication defined and the normal vector addition. How can I do that? Well, I have to find a property that it fails. Okay, when you're trying to pick the right property to check, because you don't want to check all of them, because it could just be one property it fails. You don't want to have to check 9 to see that they all the other properties hold. So how we're going to try to eliminate some of the properties we need to check. Since we're using normal vector addition, anything just involving addition you probably shouldn't check, because if we had normal addition, then this is a vector space, so we don't really need to check that. Anything involving scalar multiplication, because this is a very strange scalar multiplication, that's what we want to look at. And it will actually be kind of hard. I'm going to tell you which one it is. Maybe you should try it for yourself and see if you can find a property it fails. So maybe pause the video and try to work on this. Okay, let me show you a property it fails. So we had this property that says if we take two scalars and add them together and then multiply it with the vector, it's the same thing as multiplying each of the scalars with the vector and then adding them. Let's put this funny looking multiplication here. It fails this property, and let's see it. So let's choose a number. Let's actually choose a number that is an integer when we add these two together. So let's go with 3.1 plus 3.9. And let's choose for our integer 1. Okay, let's use our definition of scalar multiplication. Well, this is equal to 3.1 times 1, where we take the greatest integer here, plus 3.9 times 1, this is equal to 3 times 1 plus 3 times 1, which is 6. So 6 is equal to this side. Now what is the left-hand side? Well, 3.1 plus 3.9 times 1. Well, let's write that out. The left-hand side is 7 times 1 in this fancy multiplication, which is the greatest integer involving 7 times 1, but that's just 7. So we get 7, and scrolling back up here, this is equal to 7, and 7 is not equal to 6. So it fails this distributive property when it comes to scalar multiplication, so it is not a vector space.